Hello, in this tutorial I'm going to explain how to convert from decimal to hexadecimal in a very simple way. To begin with, let's be really clear on exactly what we mean by the word decimal and the word hexadecimal. Now, first of all, if you look at the word decimal, you can see that the beginning part of it looks familiar. For example, we have decimal and we have decade and decagon and so forth, which all refers to the number 10. You can see that hexadecimal has DEC in it as well, dec, but it also has HEX, which you might well remember from words such as hexagon. So that is, of course, 6. So decimal is something to do with the number 10, hexadecimal is something to do with 6 and 10, which is, of course, 16. So hexadecimal is something to do with 16, whereas decimal is something to do with 10. So exactly what is it to do with? Well, decimal, of course, is counting using 10 digits. And these are the digits from 0 to 9. And we can count any number at all that we like using just those digits. If we have the number 123, we know that that's 3 lots of 1, 2 lots of 10, and 1 lot of 100. And this is the sort of place value table that you learnt about when you were very young. So we always start with our units on the right, and then we multiply that by 10 to get our tens column. Then we multiply by that by 10 again to get our hundreds and our thousands. So each time we move one place to the left, we're going to be multiplying the units by 10. And so that gives us the ability to create any number using the digits 0 to 9 as long as we want. So how does it work in hexadecimal, and what exactly is hexadecimal counting? Well, we know that hexadecimal is something to do with 16, and in fact it is counting using 16 digits, which sounds confusing because of course we only know the digits 0 to 9. So how can you have a digit that goes beyond 9? And of course the answer is not 10, because that's not a digit, that's 2 digits, 0 units, 110. So that's not the answer. The answer in fact is that we start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we keep going using letters A, B, C, D, E, and F. So if we're counting, 0 to 9 is exactly the same in hexadecimal as it is in decimal, but then we have 10, 11, 12, 13, 14, and 15. So the value of F is equivalent to the value 15 in decimal. Now that might sound a little bit confusing, and you might wonder why on earth computer scientists have such a numbering system like this. And the answer in fact is that it makes life a lot easier. Why does it make it easier? Well, think of it this way. If we have a binary number, let's say the number 1, 1, 1, 1, 1, 1, 1, 1. Now, when you get a number that's, in this case, 8 digits long, unless it's really easy to remember, like this, it's all ones, it can get very confusing. Human beings do find it confusing when you're faced with a number that is a lot of ones and zeros. Now, that, of course, is counting using just 2 digits, 0 and 1 in binary. If we're using 10 digits, 0 to 9, in decimal, then that number becomes 255. Notice how much shorter it is in length. Here we have 8 digits, in base 10 or decimal, only 3 digits. And if we're going to go to hexadecimal, which uses 16 digits, that number becomes even shorter again, and it's simply the number FF. So effectively, the more digits you have in a counting system, the shorter the numbers themselves will be. So only 2 digits, 8 numbers long. 10 digits, only 3 digits long. 16, only 2. So one of the reasons in which hexadecimal counting makes it much easier for us is that the numbers themselves are much shorter, and therefore they're easier to enter, easier to read, and you're less likely to make a mistake. But of course it's also true that the fact that you have letters inside these numbers can also make it easier to remember, and in fact computer engineers has often used this fact to deliberately construct values in code or in error messages which read as real words. For example, Microsoft Windows, when it crashes, if it ever crashes, can or has in the past produced a blue screen of death, and one of the error codes for that was a hexadecimal number. So D and E and A, and then D, C, 0, D, E, which of course is pretty easy to recognize and remember. So when you're using hexadecimal, the numbers themselves are very short, and in fact the numbers themselves are easier to read and remember as well. So that's in a nutshell what hexadecimal is and why we use hexadecimal. But how do you convert from decimal to hexadecimal? Well, there are a couple of ways, and one of them is a little more complicated than the other. So the way I'm going to show you is very simple. And in fact, it's so simple. I've taught this for years, and I've had students who have, within a very short space of time, been able to now start converting decimal numbers to hexadecimal in their head. It's that straightforward. So let's start off then with the main secret, and that is when you're converting from decimal to hexadecimal, you in fact don't go directly from one to the other. What you do is you go through binary. So you're converting decimal to binary first, and then you're converting the binary into hexadecimal. Now that does seem like it's an extra stage. How can that possibly make it easier? Well, this is how to do it. Let's start off with the number 123, and that is base 10 or decimal, so I'm just going to put the little number 10 as the subtext notation there to show which counting system that number is in. So that is decimal 123. Let's now convert that number into binary. So to do that, of course, we need our place value table. And just as with base 10, we start off with a 1. But this time, because we're only using 2 digits, not 10, we're not multiplying by 10 each time we move to the left. We're multiplying instead by 2, because there are 2 digits. So we start with 1, multiplied by 2, and the next column is 2. Then it's 4. 8, 16, 32, 64, and finally 128. Well, it's not the final place value, but it's the 8th column, and very often when we are using binary, when we're working out binary numbers, we will certainly be using 8 columns, because 8 bits, 8 binary digits, is known as a byte, a word you may have heard of, may be familiar with, and a byte is an 8-digit binary number. So now we've got our place value set up. What we need to do is to work out now how to turn this number 123 into binary. We've only got the digits 0 and 1. Those are the only 2 digits we can use. So all we can do is put a 0 or a 1 in these columns. So the easiest thing to do is to start with the ones. We can only have one of each of these numbers. So which of these numbers will I use in order to make 123? Well, I'll certainly not want the 128 because that's too big. Well, I can put a 0 there to start with because I know I don't need that one. 64 is the next biggest number, so I'm certainly going to need that, and I'm also going to need the 32 because if I add those two numbers together, I get 96. 96, yeah, we're going to need a 16, so 96. And the 10 is going to be 106 plus the 6, 112. And something that I recommend to my students is at this point, when you've started to get close to your target number, rather than adding on these numbers, simply work out what you're missing. So here we have 112 so far. We're aiming for 123, which means we're missing 11. So now, instead of working out what 123 is, we can work out what 11 is. And 11, of course, is simply an 8, a 2, and a 1. So we'll put a 1 under those columns, fill any other column we've not used with a 0, and there we are. That's now converted the number 123 in decimal to the binary number 01111011. Okay, so now we've done the hard part, the first part, and we have converted the decimal number into binary. What do we do next? Well, in fact, what we're going to do is we're going to split this 8-bit binary number into two separate numbers. So I'm going to draw a line straight down the middle here, not a very even line, but nonetheless, that'll do. So we divide this number into two. So we have the number on the right here, 1011, and the number on the left, 0111. Now, if this number here on the left is a completely separate number, these place values aren't right. Because obviously, if this is a complete number, 0111, this one here is in the units column. And that's not the units. So we'll have to renumber these place value columns. So if this is a completely separate number to the one on the right, then our place value will start again with 1, 2, 4, 8. So now we've got two numbers, and by the way, these separate numbers, half a byte, are called nibbles. So a byte is 8 ones and zeros, and half a byte is a nibble. And I'm not trying to wind you up, that is in fact true. So we have two nibbles here. We need to now convert each nibble into hexadecimal, which is very, very simple, because all we need to think about is the fact that hexadecimal goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So all we're going to do is work out what the value of this number is using these place values, and then see where that number appears on this line. So let's have a look at this. We've got a 1 in the 4 column, we've got a 1 in the 2 column, and we have a 1 in the 1 column. So we have to add these three columns together. So 4 plus 2 plus 1 is of course 7. And 7 is on this line. There it is, no problem at all. So that means that that is equivalent to 7. Let's have a look at the one on the right now. So here we have a 1 in the 8's column, a 1 in the 2's column, and a 1 in the 1's column. So we add the 8, the 2, and the 1, which of course makes the number 11. But 11 is not one of the digits in hexadecimal. So which position is it? Well, we've got 7, 8, 9, 10, 11. So that, the letter B, is the value of 11. So we write down B. And that's it. That's our answer. So 123 in decimal is 7B in hexadecimal. It's as simple as that. I'll do one more to demonstrate that again. So let's just clear all of this. So let's clear all that. And let's try now the number 233. So if you've got a bit of paper or a whiteboard or something, you could try doing this along at the same time. And possibly you might want to pause the video just so that you can have a go at each stage. So the first step is, of course, to create our binary place value. So we've got our 1, 2, 4, 8, 16, 32, 64, and 128. And we're going to now convert 233 in decimal into binary first of all. So if you want to have a go at this yourself, and you've got a bit of paper handy, have a go at doing this, pause the video, and when you're ready, when you think you know what the answer is, come back to the video and we'll see whether you got it right. Okay then, so either you've had a go at it, or you are deciding just not to bother and to watch the video. So let's see how we can add these up. We start on the left, and clearly 128 is going to fit into 233, so we definitely want that. What about 64? Well, 128 and 64, 60 and 20 is 80, 88, 92, 192. So we know we've got 192 so far if we have a 64, so that's absolutely fine. What about a 32? Well, yes, that's definitely going to fit because, 32 would fit into it even if we're up to 200. So what's 32 and 192? Well, add the 2's, 194. Add the 30, 224. So 224. So we want one of those. And as I said the first time round, if you want to make sure that it's a little easier at this point, we know we're getting very close to our target, so just simply work out what's missing at this point. So we got 6 to 30 plus the 3 makes 9. So how do we make 9? It is of course the 8 and the 1. Fill all the rest in with zeros, which means that our answer is 1110 1001. That's the answer. So did you get it right? If you did get it right, put a comment down below. Let me know that you got that right, and that'd be fantastic. But we are only partway there, of course. So the next step is to divide this byte into 2 nibbles. So we need to divide it down in the middle there. So we have 4 digits on the right, 4 digits on the left. But now, of course, these values along the top are wrong, because we never start on the right hand side of a number with the 16s column. It's always the units on the right. So we have to now replace each of these place values, because this number on the left is totally separate from the number on the right. So just as we have 1, 2, 4, 8, we need to have 1, 2, 4, 8 as our columns here. Now, at the bottom, we can write out our numbering if you want to. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And if you are revising this for an exam, which is very likely, I would recommend that you actually write that number line out in the exam. Yes, it seems obvious, but it's surprising when you're in the exam room that your brain can start relaxing when it thinks, oh, this is so easy, I don't need to worry. And that's when you can make a silly mistake. And I've seen it happen many, many times in the classroom and sadly in exams occasionally. So it's really important, I think, to give yourself the best chance of getting this right and not making one of those silly mistakes, because you've done all the hard work and this was the easy bit, and bang, that's now thrown you. So write that number line out so that we can just simply work this out really easily. So again, what you might want to do now is to pause the video in a second. We're going to take this this nibble of data on the left, and we're going to convert that into the first digit of our hexadecimal number, and then we're going to take the number on the right and convert that into the other hexadecimal digit. So if you want to have a go at doing this yourself, then pause the video now, and I'll see you in a second. And either you've had a go at that and you now have the final answer, or again, you're sitting there thinking yourself very smug because you either did it in your head or you're letting everyone else have a go. But here we are. This number then is, let's add these columns up. We've got an 8, we've got a 4, and we've got a 2. Those are where the ones are. So 8 plus 4 plus 2 is, of course, 14. Now, 14 is definitely not in this number line. So where is it? So let's start 7, 8, 9, 10, 11, 12, 13, 14. That gives us E. So we know that the left-hand digit is E. And let's have a look at the right-hand side. So we have a 1 under the 8. We have a 1 under the 1. So 8 and 1 makes 9. Nice and simple. So the answer then, 233 in base 10, is E9 in base 16. So there we are. It's a straightforward way of converting from decimal to hexadecimal. And in both those examples, you can see how we had a 3-digit number in decimal, which ended up as a 2-digit number in hexadecimal. So you can see, even with quite small numbers relatively here, that hexadecimal gives us shorter numbers, easier numbers perhaps to remember, and when you're entering data in a computer, you're less likely to make an error when you're entering those numbers. So if you got either of those questions, either of these stages right, then do please leave a comment below and let me know. If you're a little bit confused still, not entirely sure about it, and you'd like some more help, do feel free to pop a question in the comments and I'll have a look at that and try and support you, try and get you through that. If you found this video useful, then that would be fantastic if you want to leave a comment to let me know that. And it would be really appreciated if you could give me a thumbs up. Thank you very much indeed. If you do, that would make me very happy indeed. And of course also, if you have not yet subscribed, click the subscribe button, and then you'll be the first to know when new video tutorials go live. If you have any other topics for perhaps a GCSE course that you're studying that you would like some help with, do leave a comment and let me know, and I will do my best to try and get those done for you. So thank you very much indeed for watching. Leave a like, leave a comment and subscribe, and I'll see you in the next video. Bye for now.